So our speaker is Professor Alex Babanin. He's a professor in ocean engineering and the director of the Centre for Disaster Management and Public Safety at the University of Melbourne. He's had a long and, well, I don't want to say long in a bad way, but distinguished career, judging by his resume. So he's worked as a research scientist in the Marine Hydrophysical Institute in Sebastopol, as an academic at the University of New South Wales at ADFA, at the University of Adelaide, and at Swinburne University of Technology. His areas of expertise, research and teaching are wind-generated waves, maritime, coastal and Arctic engineering, air-sea interactions, ocean turbulence and ocean dynamics, climate, environmental instrumentation and remote sensing of the ocean. Quite an expansive area of areas of interest there. So without further ado, I'm going to hand over to Alex, and please take note of any questions you have as we go along, and we'll get to those towards the end of the presentation. Thank you. Over to you, Alex.
Thank you, Tom. Thank you for introduction, and to Carl for inviting me. It's a great pleasure and honor to be speaker at the ARENA seminar series. And I'm an ocean engineer, but not naval architect. My area is Metocean engineering, and I will define it more accurately in the subsequent slides. But if I were to define that in just one sentence, I would say that 70% of research which we do is about the ocean waves. And I presume that links us with the naval applications and naval architecture, where the waves must be a big contributor as well. So I will speak about what I know best about my research, but I will try to keep in mind and put into perspective of a naval architecture. But I don't judge me too severely, right? If I say something naive here. But let me start from a little bit of the promotion of our field, which is your field as well, the ocean science and engineering. And my first quote is from an article by a NASA publication. And NASA is a space agency. And the article was called The Great Unknown. And it was saying that even with all the technology that we have today, that's exact quote, right? Satellites, buoys, underwater vehicles, and ships, we have better maps for the surface of Mars and the moon than we do for the bottom of the ocean, right? So there is plenty of challenges in our profession, but this makes it interesting as well. So the ocean scientists work with one of the most complex environments in the universe, right? I mean that, right? I say that when I talk to astrophysicists and astronomers as well, right? If we think of waves, right? The wind-generated waves, for example, that's the greatest challenge and most complex challenge which you can imagine, right? They are generated by the wind, and the wind must be turbulent to generate the waves, but there is no theory of turbulence to begin with. Right, the way the waves develop require both very strong nonlinear interactions, like those due to wave breaking, and very weak, like the third-order resonant interactions in the hydrodynamic equations, both of them at the same time, right? So analytically, it's just incredible challenge. And then just to keep the balance in the system, because no matter how long when the wind blows, the waves never grow 1 kilometer high, the wind-generated waves, right? There is a dissipation in the system, and that's due to the wave breaking mostly. And the wave breaking doesn't even cover the entire two-dimensional surface. It has fractal distribution, right? It's here and there, 1 out of 50 out of 100 waves, which is breaking, and that's enough to keep the balance in the system of the waves development and the wave growth, right? So the equations which supposedly, when they develop eventually and describe the white capping and the wave breaking wouldn't even cover the two-dimensional surface, and we don't have that kind of equations in hydrodynamics. So bring that all together, and that's the absolute minimum, right? The wind input in nonlinear interactions and the white capping dissipation. It's just the bare minimum which you need to describe the waves and be able to predict them, right? And each of them is a challenge in its own right of great magnitude, right? And now obviously we need forecast, we need hindcast, we need some characteristics for any design and any operations which we do at the ocean. So we need somehow to deal with all those challenges. Now, if we talk about the oceans and the waves in that system in the context of, say, the global climate, right? Climate is something which we perceive happening to the atmosphere. So it's warming or something else happens to it. The whole heat content of the dry atmosphere is only 2 or 3 meters of the heat content of the ocean water, right? So the ocean, which is on average 4 kilometers deep, has an enormous heat capacity by comparison with the atmosphere. So by doing something inaccurate in our predictions of what happens to the ocean, right? We can freeze atmosphere instead of warming it, right? That's how important the knowledge of our ocean science is, right? And we deal with that. Now, coming back to the ocean engineering, it's an extremely aggressive environment, right? You know more than me about that, of course, corrosion and other things. One example which I always give to the students when starting talking with them in the beginning of the course, right, that if you are a spacecraft engineer, right, the pressure difference which you deal with is 1 atmosphere, right? Is on the spacecraft inside it is 1 atmospheric 1 atmosphere pressure, and the outside is 0, so its difference is 1 atmosphere, right? But in the ocean, 10 meters of the ocean water produce 1 atmospheric pressure, right? So if you go down to the bottom of the ocean, 4 kilometers or even 10 kilometers, right? Well, that's a thousand atmospheres, right? And that is an engineering challenge on top of everything else, right? And this is our science, and this is our engineering where we work it and love it. So a few pictures which relate closer to mid-ocean engineering, to the influences of mid-ocean environments on the engineering structures. To introduce the topic closer, starting from the top left, that's the oil rig, an oil rig in the North Sea. The lower deck is 20 meters above the mean water level. The wave is breaking, and the wave is nearly getting there, right? It's 20-meter high wave, and it's breaking. And when the wave is breaking, the water is moving with the speed of the wave, which is 10 of meters per second, right? And 1 cubic meter of water weighs a ton. That's kind of the loads on the structures due to mid-ocean environments we're having in the ocean. Going down this column, right? These are structures in the ocean below the surface, right? They go, these kind of platforms go all the way to the bottom. They have to interact with the soil, geotechnical issues. There are anchors there, and so on. Down at the bottom, there is a ship. It's an artist impression, but probably close enough to what happens in reality. A ship is meeting a freak wave or rogue wave, as they are called, right? And we will return to this kind of waves later on. And the next row in the middle, that's the waves in the coastal environments, the 2 pictures on the top, right? And I mentioned wave breaking already a couple of times. That's quite special phenomena in mid-ocean engineering, right? That's how the waves lose their energy. They accumulate energy slowly under the action of the wind, over kilometers of the wave action, or tens of kilometers of the wave action, and hundreds or even thousands of wave periods of the wind action. Sorry, not the wave, the wind action. They accumulate slowly the energy, the waves, and then they lose it rapidly in the wave breaking event within a fraction of the wave period, right? And in the open ocean, that happens every now and then. 1 out of 100 of waves which are breaking at the coastal areas, all of them are breaking eventually, right? And release all that energy. And for the coastal structures, they have to withstand that energy. That's what they designed for, right? You see the breakwater there and the lighthouse. And you see an enormous wave in the middle picture. This is not a Photoshop. This is really what the waves are like when they channel. This is a village channeled, focused by an underwater canyon. This is a village in Portugal. Now, in ocean engineering these days, Arctic engineering is becoming an interesting and important component. The Arctic Ocean opens of ice in summer, becomes available for a navigation in summer months, and then the ice, which is refreezes in the winter, is the first year ice, so it's not as thick as it used to be, and navigation is possible even for ships with stronger hulls, not necessarily the icebreakers. And what you see is a port, Sibeta port, built in the middle of the Russian Arctic in Siberia, right? That's the oil and gas port and facilities are there. This is also part of ocean engineering these days. On the top right is dredging application. We all know about that, of course, and the massive infrastructure developments which happen in the Gulf countries. For example, that's the next picture. And at the very bottom, you see our very own Port Phillip Bay, a satellite picture of Port Phillip Bay, ocean color, right? And the ocean color here is, it can show you the chlorophyll or whatever other biological elements distributed on the surface. But in this case, it shows distribution of the sediment suspended after the storm, right? And we all live in Melbourne, and we remember the issues with the dredging, which happens every now and then in the channel which leads up to the Melbourne port, right? And there are always discussions about the sediment suspended turbidity of the water due to dredging. And here is the sediment suspended due to just regular Metocean forcing, right? The wave action in the lee of the storm. And we can see that from the satellites, concentrations are similar to the dredging, right? Except the causes are natural. And this is a regular event. And as I said, we see that from the satellites. And that's the part of the ocean engineering now, because satellites give us these capabilities globally, and they go into the past now because satellites have been around for 40 years. Very briefly about coastal engineering, which is also part of our research, maybe not less relevant for naval architects. Right, what are the coastal engineering subjects? This is the sediment transport in the first place, and you see the coastal erosion at Collaroy Beach in New South Wales after the infamous storm. Down on the left, there is impact of Hurricane Katrina on New Orleans. Also, we all remember that. But that part was not, the destruction was not due to the hurricane, but due to the storm surge in the ocean, which damaged the dikes, and then the flooding happens, right? The landfall of Hurricane Katrina happened elsewhere. Now back to the Arctic. In the Arctic, which was frozen for thousands of years and now is subject to the wave action. Again, waves cause coastal corrosion in some places at enormous rate. It's the retrieval of the coastline is hundreds of meters per year, right? And entire townships have to be moved because of that. At the bottom right, you see in Adelaide Beach, and there was a breakwater built in front of the beach to protect the beach and the properties behind that. And then the beach started building up behind the breakwater until it was washed away by a strong storm again. And this is a mobile area where the ocean interacts with the beach, and this is also area of research and application of us. who work as an ocean engineer, except this is coastal engineering and the applications are very different there to the loads on structures or on ships in the ocean. So I promised a definition of Metocean engineering, this one I took from Wikipedia. It's the syllabic abbreviation of meteorology and physical oceanography. Basically, when we predict the weather inland, we predict what happens in the atmosphere, right? But when we do that in the ocean, atmosphere is not enough. In fact, most of the loads on the structures, and I presume on the ships as well, in the ocean comes not from the winds, which are only 10%, but rather from the waves, which are about 70%, and from the currents, about 20%. That's roughly, right? So let's imagine the tropical cyclone or hurricane, as they're called in America, enormous winds, and still that's only 10% of the loads. The 70%, if you're near the surface and affected by the waves, that's from the waves. That is why it's so important to understand them, to be able to predict them, and put that knowledge into design. Now, how we study them, there's plenty of research instruments these days, and I would say along during my career, that was 20 plus years, close to 30 probably now. It's all sorts of instruments came into existence which we didn't even hear about, didn't even think about when I was a PhD student. Acoustic, infrared, optical, and other physical signatures of Metocean phenomena can be used. We use them now. And the Metocean research links fundamental physics and earth sciences with ocean engineering and other offshore applications. Fundamental science, fluid mechanics, right? Fluid mechanics is as fundamental as it is. In the 19th century, that was almost a synonym of mathematics itself, right? And obviously, if we want to understand the motions of the surface, wave motions, right? Fluid mechanics, that's where we start. But oceanography, marine meteorology, much more complicated than that. So there's a lot of parameterization still going on. There, it's a long way to be exact science for oceanographers. Exact science like fluid mechanics or physics or mathematics. Ocean climate is a science in its own right these days, and a number of specialized technological disciplines for in situ and remote sensing observations. What do we need the Metocean knowledge for? I alluded to that a number of times already, just a few pictures to support that. Design on the left in the first place, that's an oil rig, right? And there is a bridge between the two rigs, right? Obviously, those have to be built above the maximal wave height, right? Because as I said, the water is very heavy. If it's moving, it will just carry away that bridge, right? At the same time, you don't want to build it very high, right? Because that's very expensive. So knowledge of Metocean climate is very important in the design. I don't need to tell you much about its importance in operations and logistics. And my pictures here are from the offshore applications, and that's operation of the supply ships and the supply helicopters. It's important in the construction, right? And this picture on the bottom left shows how you carry a fragment of an oil rig to a deployment and to maintenance. And that's a schematics, which shows a complex of FPSO, which connects it to the pipelines at the bottom, to drills, to anchors, risers connected to the platforms, and so on. Everything here implies and requires the Metocean knowledge, and this is what our research is about. I also let myself to speculate or dream a little bit about the future of the ocean engineering for this talk. And there is some future which is already happening, like a FPSO on the left, or offshore windmills. The FPSO, we already have them in Australia. Offshore windmills, they're more common in Europe, but they're coming here to Australia as well, even to Victoria. Right, in the Arctic, there are oil rigs. They're already out in the ocean, right? And once you are there, you have to deal with the ice, not just with the waves and the currents and the winds. And if the ice is moving, even under the action of the wind, the whole ice field, that can put a lot of stress on any structure which is in its way. In the deep water, our oil rigs, which used to just rest on the bottom, now they go into real deep water where they cannot just be put on the bottom, so they have to be floating, and that's a whole new level of interesting and challenging engineering application. And again, this is already happening, and the bottom right picture, the distant offshore, that's the distant future, right? I presume when we go into the really deep waters, everything will be difficult to supply energy, cables, pipelines very far in the ocean. So that would have to rest like even the power stations at the bottom. And that is the ultimate ocean engineering challenge. Now back to our research, right? And I have to move around something on my screen so that I can see the top of the screen. There is a lot of bullet points, and I'm not going to bother you with reading all of them, but basically, as Tom mentioned in the introduction, we cover a lot of Metocean applications. We try and cover all of them. Wind-generated waves are in the center of that. And that brings us into the ocean engineering, into the air-sea interactions, into dynamics of the upper ocean, including the ocean turbulence and ocean mixing, into the climate, and of course, in instrumentation and methods, right? Because if you're doing the cutting-edge research, there is not always that you can buy some measurement devices off the shelf. You have to design them yourself. Our facilities, at the top right, you have you see the observational site, which is maintained by Woodside. The air-sea interaction from one of the oil rig, and we established, and that was the first in the world, and perhaps remains the most sophisticated air-sea interaction site, where we measure everything in the atmospheric boundary layer, on the surface, all the fluxes, and below the surface. And because Australian oil rigs in the northwestern shelf are in the path of the tropical cyclones, then we can measure these air-sea interactions in the tropical cyclones, which is still an ultimate challenge for the forecast. That's where the predictions often fail, in spite of enormous attention research community over last couple of decades. So the tropical cyclones are principally an air-sea interaction phenomena, and obviously some knowledge of that is still missing, and this side helps us to work with those. And the top left, you see a track of one of the cyclones which was going along the coast of northwestern shelf, and then turned towards the platform where we have the observations. The platform, of course, can be evacuated, right? But it's still there, unlike the ships, which usually, if they know that the cyclone is coming their way, try to avoid that. Now, tropical cyclones is an extreme in the mid-ocean context, but swell is another extreme, right? Swell, you think of swell, that's the waves which are not that steep, they're not breaking, right? But they can be a challenge in the ship operation, in the side-by-side ship operation, or for tankers. And with swell prediction, like with the tropical cyclones, right, we have major problems. So the models which predict the waves, forecast the waves, they don't do particularly well with the swells. And that's not just the wave height, but also the swell arrival time, right? Swell, by comparison with the models, can be very early or very late. And in order to understand that, we need to measure that. And on the bottom left, where you see are a set of buoys along the coast of South America. That's not our buoys, but we collaborate closely for many years now with researchers from Brazil and Argentina. And this way, we have access to facilities which allow us to deal with this another end of environmental of mid-ocean extremes. Now, satellites, I mentioned them already a few times today, and that's for a reason, because once they appeared, they really changed the oceanographic observations. In the past, that would be just buoys or ships, which then provide detailed but just one point measurements, right? Satellites provide global coverage, not the same high resolution as in situ measurements, but global. And you see the schematics of how long the satellites, which measure the winds and waves, are available, and that's starting from 1985 now, right? And 6 altimeters are flying now. Right, so we can look not only at the global properties of waves and winds, but also how they have been changing over the last 40 years. So that's really a revolution which happened in wave and in mid-ocean research with the remote sensing from the satellites. Now, polar deployments, which we do, and I said that the Arctic engineering became a hot topic, if I can say that, about this very cold environment over the last 10, 15 years. And we participated in a number of complex expeditions, like the top left, funded by the US Office of Naval Research, and complex projects in the Arctic, and also continue our research in collaboration and sponsored by the Australian Antarctic Division in Antarctica, top bottom left. And on the right, you see a few pictures, including myself. That's the figure on the left. Looking at trying to choose a site for a wave ice interaction observations in Spitsbergen in the Arctic. It's an archipelago in the Arctic, 78 degrees north, just 1,200 kilometers from the pole. And this is a picture from our buoy. Just wanted to show you a nice picture. We deployed the buoys in Antarctica, right, measuring the waves, sitting on the ice, and this is an orange buoy, so it attracts penguins, which come to see what it is, right? And the buoy, apart from scientific measurements, also does take pictures of what's happening around, so that we can correlate them later. Now, how do we study the waves? Fundamental science drives that, of course, and for that you need to understand and develop the analytical theories and test them in the numerical models. And we developed the fully nonlinear phase resolving models which simulate the waves explicitly in our group. And just a few illustrations of those. I started a video now of what is a fully nonlinear three-dimensional wave model, right? And these models, which we develop for research purposes, are available for applications, right? These are open source models. So if you're interested in this kind of modeling, just talk to me and we'll share these models with you. So they model directional waves on the surface, which is two-dimensional, as you can see, and they also have a third dimension, so they extend into the water column. Now, in order to understand how the waves develop and are generated, we need to have models for the wind wave interactions, and that's another video which I started. What you see in the air is the tracers. They are just to illustrate what happens in the wind above the waves, and wind generate the waves, but you can see that the waves affect the wind. There is a full flow separation and turbulence and so on. On the top, you see a few pictures. One of them is the vertical slice of the wave kinematics. The wave orbital motions extend for the surface waves extend into the water column at the scale of the wavelength. So if in the ocean that scale is 200 meters, so about 100 meters below the water surface, you would feel the wave orbits. And usually we teach the linear theory and it just extends vertically. But if you can follow my cursor, you see that for nonlinear waves, the wave orbital motion is related to the surface, but is not a vertical distribution of what you see on the surface. The bottom of the wavy column comes first, right? So if we're talking about the loads on the structures, right, that's not a simultaneous heat. The bottom of the wave comes first, and then comes the surface wave, which in this case, in this picture, is breaking. We model the all sorts of air sea interactions, and you see a model of a tropical cyclone. Tropical cyclone feeds on the energy of the warm ocean. So the ocean must be warm for the cyclone to intensify, but it comes also with the strong winds which generate big waves, and the waves can mix the ocean, and ocean is cold down there, and then it can involve colder waters and cool the surface and impact on the intensity of the tropical cyclone, something that we still don't predict very well. And this is an impact of the wave on the sea surface temperature that you see based on our models in the middle picture. And the wave-induced turbulence, again, another model for wave interactions now with the water is on the right. That's among the models which we develop in our research group for all sorts of research that we are using. Now, when we deal with the ocean waves, and I have no doubts that you know that better than me, we deal with the spectrum of the waves, right? In the fluid mechanics, we like to use sinusoidal waves, one-dimensional usually, right? Real waves are not like that. At the top left, you see the picture of a real wave surface. That's not even some big storm. The waves are directional. There is some mean direction following the wind, but the waves also come from other directions, oblique to the main direction. They break in here and there, and that's the a surface which we have to deal with. And over here, you also see the waves, the very big storm, the rogue wave, the hurricane from the top. You see how peculiar is a picture of the waves in the hurricane. There's enormous coastal wave. On the top right, you see a coastal guard going against the current, right? So it's not some rogue wave, it's just a regular thing which they do every morning at the mouth of Colombo River in it's not California, what is the Washington State, right? Then there are the waves in the ice, right? When the ice is just freezing, and capillary waves, which are used for the remote sensing of the ocean. So we have to deal with all sorts of these waves when describing them, not in fluid mechanics, but in the ocean applications. And for that, we use completely different set of models. We use spectral wave models. And again, we have physics for the spectral wave models, which we developed in our group. Before I outline that, I want to introduce the spectrum just very briefly, just in case there is somebody who is not familiar with this concept. The spectrum, and I borrowed this picture from an old paper by a monk in 1950. This picture is borrowed from a book of Leo Halhuisen, right? Who borrowed it from the monk's paper. The vertical scale here is the energy scale, arbitrary, and the horizontal scale is the wave periods, right? At the top right, at the distant right, it's the short wave periods or the high wave frequencies. 0.1 second is the shortest wave period shown here, and going to the left is the longer wave periods. So the wind-generated waves are sitting here. These are the waves with the periods between 0.1 second and 10 seconds, right? And the peaks show the corresponding wave energy within those wave periods. This is our spectrum. It shows distribution of the wave energy along the frequencies. And then the longer waves are on the left. That's infragravity waves, which we usually have generated in the coastal areas and in the ports. Tsunamis are even longer, and seishes, storm surges and tides, and so on. And then the waves are also directional, right? The simplest directional representation, directional spectra, is the top left picture. That's two swell trains coming from two different directions perpendicular to each other, and therefore you see this nice rectangular picture. Then the stormy waves, and kind of you can guess where the main direction of the waves is, but the waves also come at oblique angles. The hurricane waves over here, and you see the directional waves due to a different reason, due to the gas of the winds, which creates this kind of directional crest. And for nonlinear waves, and the last picture here is from the wave tank. The waves, even perfectly unidirectional, so produced by the wave maker and moving into a single direction, can develop the directional structure for their crests if they're steep enough, so if they are nonlinear. And we have to put that all together into a concept of the spectrum, right? And this is how it is done. The yellow line is some arbitrary surface movements, and we fit some sinusoidal waves there and allocate them with amplitudes. And in case of the continuous spectrum with the energy density at this particular frequency or this particular period. And like shown for the directional wave on the top left, we put this kind of unidirectional and uniform waves with particular periods on top of each other, and produce a complex C in the end. And integral of this spectrum gives us the wave height, significant wave height. Integral of the spectrum is basically significant wave height squared. And this is the property, the basic property, which we use for analysis of everything. But if we want to split that out into contributions at different wave scales and different directions, we can do that with the spectrum. And spectrum, this is what we predict in the wave forecast models, right? That's the spectral models. And the notion of the spectral model is shown here. On the left, we have the full derivative of the wave spectrum. The wave spectrum shows us distribution of the wave energy along the wave numbers or the wavelengths, the frequencies or the wave periods, the directions, and this spectrum also changes in space and time. So the full derivative takes account for that. Currents, refraction, diffraction, everything is there. If you integrate the full spectrum, you get the total wave energy, right? So it's derivative, so it shows how the wave energy changes in time and in space. So on the right-hand side, you see the sources and sinks of that wave energy, right? So that's how much energy gets into the wave field over a unit of time. That's the energy input from the wind. How much of energy gets out of the wave field per time? That's the dissipation, and that can be due to breaking or due to interaction with adverse winds or due to producing turbulence in the water and so on. And there is nonlinear interaction term, and there is a term responsible for interactions with the bottom when the waves become shallow. This is what the spectral models do, right? They don't predict individual waves, they predict the spectra. And as you can imagine, each of those terms is a complicated expression which reflects very complex physics in its own right. So we measured all those terms, right? And this is an illustration of our measurements of the wind input. On the left, you see myself and Mark Donovan from the University of Miami, 25 years younger. And on the right is the wave follower. And the key here is this pressure sensor, which is very close to the surface because it has to measure the pressure induced by the waves in the wind, very close to the surface, preferably below the wave crest, but the pressure sensor has to stay dry, otherwise it fails, right? So we did this kind of measurements and we built up the parameterizations of all the source functions based on observations for the first time, and we implemented them in official releases of all the modern third generation wave forecast models, including WaveWatch 3, which is American model and also used by the Australian Bureau of Meteorology, SWAN, which is European Coastal Engineering Model, WAM, which is global model used by European Center for the Weather Forecast. Our source functions for the wind input, for the white cap and dissipation, for swell, for wave bottom interactions, now in these models are our physics packages there, right? And if you are using these models and would like to speak with me on any aspects relating to the physics of these models, I'm happy to do that, of course. And we continue supporting those models and developing them further. And once you have those models, you can use them for the wave forecast, of course, to predict what happens tomorrow. These models obviously depend on predictions of the wind on atmospheric models. So they give a reliable forecast up to the week ahead, probably not more than 2 weeks, but you can use them for the hindcasts, right? What happened in the past. And if you're interested in a particular area of the ocean, this is possible to do now, right? This is the hindcast illustrations of the hindcast, which we developed now for 70 years from 1950 to 2020. And I will run it again. Right, this picture shows the distribution of the wave height, significant wave height, and the wave period for a particular month. The other picture shows the distribution of the wave breaking probability, right, which is required for a number of purposes ranging from impact on structures to the gas exchange. And the bottom right picture shows distribution of Benjamin Fair index, which is used for prediction of probability of the rogue waves. Right, and here in these short movies, I only show a 1 month of this prediction for year January 2012, right? But as I said, we have this hindcast sitting on our computer here at the University of Melbourne for 70 years, and it's available for the public use, right? So if you're interested in the global climate or for that over that period of time, or over any fraction of that period of time, we can give you access to this database. It's open, as I said. Now, global wind wave climate is a new research field, and I showed you that we have hindcast of this global climate, but there are also observations of this global climate with the satellites, which, as shown in this diagram, have been flying since 1985. This is a picture of the wave trends, and at the bottom, and the wind speed trends at the top for 20 years from 1990 to 2008, right? The brown color means the growth. That's the 99th percentile significant wave height, so that's the highest wave. Brown color shows the growth by 1% per year, and you see a lot of brown color. So over this period of time, which is 25 years in this picture for the waves in some regions have grown by 25%, the extreme waves, the maximal waves, right? So this is the reality. And If you're out there in the ocean every day, you may not notice that, right? But satellites give us, and wave models these days give us this information. And obviously, that's a useful information in any long-term planning, and definitely in the design of the future applications which involve the climatology. I'll skip this slide. It shows the differences between different months, right? So you can do that not only through the years, but also over the different months. And here I'm going into my favorite topics of the wave-coupled large-scale processes, right? So we think of the waves, that's a small-scale process. Their periods are seconds and tens of seconds. Can they affect the weather, the ocean circulation, the climate? Yes, they can, right? Because they facilitate or create the fluxes across the ocean interface, right? And in the atmosphere, the waves are generated by the winds, but then they affect the very winds which produce them. And I already showed that tropical cyclones, which depend on the coupling with the warm ocean, are directly affected by the waves which are generated by these tropical cyclones, their intensity. Climate, right? It's changes happen over tens of years or hundreds of years, also affected by the waves. Why? We've just seen that the wave height has grown over the 25 years, right? The extreme wave height, but also average wave height has grown. If the waves getting bigger, they can mix more the upper ocean. Down there, the ocean is cold, so they can cool the surface, and the ocean can absorb some extra heat from the atmosphere. So these waves, which are the surface process, facilitate the air-sea exchanges and can impact the large-scale phenomena, including the climate. In the upper ocean, they are responsible for the mixing, for the heat content, and for gas exchange, even for impact on the biogeochemistry. We have a PhD. I have a PhD student now who is working on these applications, right? Because the waves produce extra mixing, which then impacts the nutrient transport, and a lot of biogeochemical exchanges and growth happens near the surface, because life needs sunshine, but it also needs nutrients, and nutrients are impacted by the waves. So that depends on the storms, on their direction, on their severity, and so on. At the surface, the waves create currents. In addition to geostrophical currents, they impact ice, they can break the ice, and all the other fluxes, gas exchange, and so on. This topic is very big, and it has kept us very busy over the last 10, 15 years, right? So I put a number of slides about that, but I suppose I have been talking already for 15 minutes, so I'd better skip some of those slides and go one of those slides, right, and go into a slide which may be of interest for you, because that has a relationship to the wave-driven dispersion. And this illustration is showing the aftermath of the MH370 accident and a surge, right? The point where presumably this plane crash happened is here in the Southern Ocean, and the search and rescue operation was going for months after that, and a lot of people say Saroa and researchers from the universities tried to predict where the debris would go, right? And this is a modeling done by Professor Chari Patirachi from the University of Western Australia, based on geostrophic currents, right? And the prediction showed that could go just about everywhere, from New Zealand to the west coast of Africa, where the debris were actually they were found, right? So the debris did go there, right? But the crash site is still under question because nothing was found, right? And when we do this kind of modeling and this kind of search, right, with the currents, with the wind influences, we miss the coupled wave influences, right? Because the waves, when they break, they create the currents which are in magnitude comparable to the surface currents due to other regions, but unrelated to the geostrophic currents, surface ocean currents, or even to the local winds. Right, and cannot be accounted for on average. They're only there if there is a storm, right? So there is really a need, not only in the climate modeling, right, or the ocean circulation modeling, but even in search and rescue, to couple our large-scale models, like the models for the surface circulation of the ocean surface currents, with the waves. And this way, we need to bring together the small-scale models and large-scale models. And that requires a good understanding of their physics, but also the numerical capabilities. And fortunately for our science, a lot of revolutions in technology happened over the recent years, and the computers these days are capable of handling simultaneously the models of such distant scales like wave models and the ocean circulation models. Now, let me put that into the perspective for the practical applications, which I promised in the beginning when I started talking about our research. So how does it relate to what we do in the practical sense? All right, we know that the main adverse Metocean influences are due to the waves, followed by the ocean currents, and followed by the surface winds. For the deep ocean operations, what are the wave influences which are of importance? Mean wave height, extreme wave height is there, of course. Wave steepness is an important property, right? Because, of course, if the wave is very long, very high, but very long, it will not do too much damage to the ship, although it can do damage to the platform, right? Because even if it is not steep enough, it can hit the platform deck from the bottom, and then it's destructive. But what is also related to the wave steepness is the wave breaking rates. And wave breaking rates, that's where the maximal wave-related loads are exposed. Right, multiple wave systems, if the waves come from different directions, are also an essential wave influence, which we have to keep in mind. And the wave climate, if we are doing long-term planning. What are the possible operational applications of these influences in a deep ocean? The mean wave properties, wave steepness, are well predicted by standard wave forecast models. Now, the rogue waves are not, but for individual wave events, the statistical methods can be used, or phase resolving models, to predict the rogue waves or their probability. And I showed you that in our hindcast, we predict the indexes which show the probability of the rogue waves. Breaking probability, if it is needed, can be made an output of standard wave models. In fact, we did it in output in our physics package, which is in WaveWatch 3, and in the latest version, you can output the breaking probability if you are using our package in WaveWatch 3. Swell is the least well-performing output of wave models, and I will return to that a little bit later. Now, the selected implications. Steepness has implications for shipbuilding. At least that's what naval architects tell me, that if a ship is intended for a particular region, then its design can be tuned to a specific steepness in that region. Wave breaking is extremely hazardous. Now, speaking of two or more wave systems, relative direction of the waves from different systems The most unsafe angles are obviously 90 degrees and 180 degrees. We all know that, but 40, 60 degrees also for different reasons, because for the wave packages, traveling at 40 to 60 degrees with respect to each other, the instability of these non-linear wave systems is the largest, and therefore the probability of the rogue waves is higher at two wave systems coming at each other at such an angle. Swell can be dangerous depending on what kind of ships is out there, and what kind of operations, like dredging, for example, or side-by-side operation. And wave climate has been changing globally. I already mentioned that. Now, the most important for operational purposes are implications of the waves and mid-ocean conditions in the deep ocean in extreme conditions. And it just happens, right? Meteorologists always knew that. In science, we get an understanding of that it winds over 30 meters per second, dynamics of the surface waves, of the atmospheric boundary layer, and of the upper ocean all change at the same time. And as a result of that, extrapolations of the models designed for regular conditions are inaccurate or even incorrect at such wind speeds. At such wind speeds, at the surface, the waves do break due to different reasons and to the normal condition, right? And that affects the prediction of the waves, because that affects the balance between of energy input due to the wind and energy output due to the dissipation. The sea drag saturates at these wind speeds, and dynamics of the upper ocean also changes. And the simultaneous change of regime in all the three air-sea environments at the same time is probably not coincidental, right? And must be happening for a reason. And in our research, we're trying to understand that. Another example of the extreme conditions is an illustration of this event near Taiwan during Typhoon Crossa. Taiwan Island is over here, and there were 3 boys measuring the waves along the east coast of Taiwan. And 2 of them measured the wave height, significant wave height of 12 meters, which is pretty high. But one of the boys measured the significant wave height of 24 meters over a short period of time, right? And why this happened? Our research in this paper showed that this is due to the superposition of 2 waves coming from different directions. There is an island, small island in front of that boy, and the waves were diffracting around those small island and focused in the location of the boy, right? That's another example of extreme conditions. And swells, right? I put them into extreme conditions. They are not that steep, maybe, right? But important across a number of applications. I was in South Korea giving a presentation to the wave community there, and I asked them what topic they want me to talk about. And out of all topics, in South Korea is subject to many typhoons, right? But they asked me to talk about swell, right? Because they have swells and they can't trust the models predicting that swell, right? And with this picture, what I wanted to show is that anecdotal evidence was coming my way. I had a student who was a surfer and would go surfing in Indonesia, and was saying that the swell, as predicted by the Wave Watch 3, is always late. The forecast is telling swell will be here today, and the surfers have to come tomorrow because today it doesn't arrive. Industry, which is subject to the same swell, on the contrary, was telling me that swell is always early, right? The forecast is that will come tomorrow, but it's coming today, right? As opposite anecdotal evidences, right? And that depends on what you expect, of course. The industry only cares if the swell comes early, so they don't regard the forecast bad if it predicts the swell too late, and the surfers the other way around. So we started looking at the swell arrival time, and the histogram over here shows you the current performance of the models which predict the swell with respect to the observations, right? And the histogram goes from -30 to 30. So according to the model predictions, the swells can be 1 day early or 1 day late by comparison with the models. And this is not a systematic error. The error changes signs, so you can't just tune the model, right? Because the swell can be early or late. And we really need to understand what is going with the swell when it propagates over very large distances from the storm which generated this swell. Now I will will be coming close to my talk. A few words about the finite depth operations, which are probably not less relevant for the Naval Architecture Society. The finite depth is where the depth is becoming comparable with the wavelength, which is, as I said, in the ocean is about 200 meters on average. The waves slow down, they become steeper, they break more often. Operational applications here, same as in deep water, and we can predict the wave height and the wavelength very well with the help of the diagrams as I show in this picture, which were developed also in our group by Professor Ian Young over this period of time. When we did have been doing the research together. In the shallow water operations, shallow waters are the areas where the depth is much smaller than the wavelengths. That's close to the beaches. Now, these areas are very different to the finite depths because the waves not just they become shorter or steeper, but the entire kinematics is different now. Instabilities are different. Some nonlinear interactions which happen in the deep water don't happen in the shallow water, but on the contrary, what is not happening in deep water, the new instabilities come to existence in the shallow waters, and we have to deal with the shallow water waves, their prediction, and using our predictions in the operations in a completely different way. And also different kind of applications become important here, like sediment transport. So implications that the waves are breaking, not more often, but all of them are breaking in the very shallow waters. Infragravity waves can associate with strong currents to the point of breaking the moorings. Such cases are known. Rip currents are produced at the beaches because of the waves disappearing and passing their momentum to the currents. Operational applications here that the spectral models are not often sufficient anymore, and then we have to do phase resolving models, and that infragravity waves and rip currents are not very well prediction. We do some exotic applications like using seismograms for detecting the waves out there in the ocean, seismic measurements, right? And these days, obviously, you almost don't need them, right? Because you measure the waves with the buoys and with satellites anyway. But the good thing about the seismic records that they go back into the 19th century, and then you can try and investigate the wave climate back more than 100 years ago when the buoys and satellites didn't exist. And conclusions, the Metocean science these days, as a result of enormous progress over the last 20 years or so, allows us to revisit traditional applications. Numerical modeling changed the nature of analytical and experimental research and of the mid-ocean forecast. Satellites, they produce revolution in oceanic applications. That's the global coverage. And now we have decades of observations, so we can see how the mid-ocean climate has been changing over the period of 40 to 70 years. No, satellites not there for 70 years, 40 years with the satellites. Now, I haven't mentioned Argo fleet. It's another evolution because the ocean is three-dimensional, and all we do is, at the best, we observe the ocean surface, but there is a third dimension, right? And it's kilometers down there. And Argo fleet, that's the boys, thousands of them are drifting now in the ocean, and they go up and down, and they measure the three-dimensional structure of the ocean, and then they surface, and then they transmit the data via satellites. So we now have a almost real-time three-dimensional picture of the ocean. And to me, that's another evolution in oceanographic observations and applications. Naval applications and operation and offshore and coastal infrastructure. For them, mid-ocean understanding is important, both in design and operations. And because it's such a complex environment, we need combined approach to attend the difficult topics. Analytical research combined with statistical methods, numerical modeling, laboratory dismembling of this phenomena, and field observations, including in situ and remote sensing.